everyone, and welcome to Exida's first 24-hour webathon. We're so happy that you're here joining us. My name is Molly O'Brien, and I'm going to be taking you through a customer journey to safe machine learning. Now, you may start off by wondering, why do we want to use machine learning in a safety-critical task? There are two key reasons why you might want to do this. The first is that you have a task that it's very difficult or impossible to perform without machine learning. Perception tasks are a great example of this. So in a perception task, you have a camera image, some kind of image, and you need to understand what's inside of this image. So you might be detecting pedestrians inside of an image for an autonomous driving task. These types of perception tasks are very difficult, if not impossible, to perform without machine learning. You could think about how could you write down a list of rules that would cover every type of pedestrian you might see in any kind of driving scenario. So for these types of tasks, machine learning is really one of the only options that you have to get useful performance. A different type of task that you might want to use machine learning in are problems where traditional approaches can't find some kind of parameterized solution. Complex control problems are a very good example of this. Often complex robot control or maybe drone control problems. It's very difficult to be able to define exactly one solution of how the agent should perform. And so this is another example of why you might want to use machine learning. So if you find yourself wanting to use machine learning in a safety critical task, there's two questions that you very likely will be asking yourself. The first is it even possible to use machine learning in a safety critical task? Is it possible to get this solution certified? And a second question is, how could Exida help me to develop dependable and safe machine learning? So for the first question, let's take a look at what the existing standards say about machine learning. It's not surprising that the existing standards we have, they weren't really written with machine learning in mind. And there's a number of working groups right now that are defining guidelines and requirements for how you could use machine learning in a safety critical task. But for now, we have the existing standards. On this slide, I've included just a couple references that our existing standards have to machine learning. So the first is ISO 26262, which is our automotive standard. They refer to the trained weights that you have inside of a machine learning model, that you can consider those to be configuration data, which are then dealt with in Part 6. The SOTIF standard, which also refers to automotive applications, they have some insight in how you could apply machine learning within the bounds of ISO 26262, and there's actually an annex that gives some implications for how you could use machine learning in a 26262 application. And the process industry, which is IEC 61508 is the standard, they have a mention that it's prohibited to use artificial intelligence for fault correction, but other than that, machine learning isn't really addressed. So without clear guidance from standards, Exida is starting by leveraging the foundations of functional safety. So we want to keep the types of techniques that we've been using in hardware and in software for many years. We want to derive requirements from our higher level system and then allocate those to our machine learning subsystems. And we want to design, verify, and validate all of our subsystems. We also, since this is such a new area, really want to emphasize expert judgment to be able to determine whether a state-of-the-art machine learning model is safe and appropriate to use in a specific application. So Exida is developing a strategy to certify some machine learning models in some applications. I want to emphasize that because we don't necessarily think it's going to be possible to certify every largest, most complex model in every totally unconstrained setting, but smaller models or models where it's possible to inspect the outputs of the model, we think that's going to be a great place to start in safety tasks. And likewise, in some applications where there can be some constraints, and there's a good understanding of when and in what types of settings the model will be working. The Exida scheme that we're developing manages risk throughout the safety lifecycle of the ML model in these safety critical tasks. And we're actually working on a pilot certification project with a 5D radar company called Provisio. And so with Provisio, we're going through these steps that we're defining in our machine learning scheme to, really see how this will apply in practical real-world tasks. And Provisio and Exida, we're both partners with Future Mobility Ireland, which is the first complete development center and testbed located in Shannon, Ireland, and it's actually right down the street of Exida's Ireland office. So we're very excited about these partnerships that we're building with machine learning. Now, for the question of how could Exida help you with safe machine learning, there's really 4 categories of services that I'd like to go over today. The first are advisory services, which guide the ML design and development. Then analysis services, which analyze the model and its performance. Then certification services, which confirm the standard requirements and Exida requirements are met. And then finally, integration services, which verify the machine learning in an integrated system. So let's start with advisory services. The first one is an ML FMEA and architecture review. So those of you who are familiar with functional safety, I'm sure you'll recognize the term FMEA as failure modes and effects analysis, which is a qualitative analysis that's done to find possible design problems, identify possible solutions, and also is used to help demonstrate compliance with standards when you eventually go for certification. These are done to find design problems early and also help keep the whole project on schedule. Now, FMEAs are very commonly done at different levels of design. So we're going to focus on specifically what's different about an ML FMEA compared to a general one. So as Exida's customer, this is what we're going to be looking for as inputs. So we're going to need the design block diagram, which at whatever level your design is, what are the key functional blocks? Where is machine learning inside of those blocks? And what are each of these blocks doing? What's the intended function? Then we also need to see what are the interfaces between your design and the external world, and what are your definitions of safe and dangerous states. Then what Exida will do is we'll help you identify how can this design fail, which are called functional failure modes. What is the impact of each of these failures? How can the machine learning itself fail? And what are the impacts of the machine learning failing? Are there ways or diagnostics or strategies to detect these different types of failures? And what's your intended operating domain? What types of settings, environmental conditions will the system and importantly the machine learning be running in? Because that can impact what the effect of these failure modes are and what possible diagnostics or mitigations you have available. So the deliverable from this ML FMEA and architecture review is going to be a comprehensive review of your ML design and early feedback on what challenges you may face in certification. And so I'll just say again, this is something that people find very helpful early in the design process because it gives them a chance to have a third-party review and get some feedback before they're too far into the design process. Another service that might be helpful from an advisory point of view is an ML process gap analysis. So Exida offers process gap analyses that look at your existing functional safety processes, but this is an analysis that's focused really on the machine learning aspects. So one of my colleagues, Dave Butler, who was great, for any of you who worked with him, you know that, he likes to say that your process is what you do and your procedure is a document that specifies what you're supposed to do. And our existing functional safety standards include process requirements to help reduce engineering errors and make sure that the design process itself is done well. A typical process gap analysis is going to look for gaps or differences between what the standard requires and what your company actually does. And the machine learning process gap analysis is really going to focus on how you do machine learning and gaps that we find between both what the standard's going to say and what Exida is going to require for safe machine learning. So, here on this slide, I'm just having a subset of inputs that we would require. This isn't everything, but the types of documents that we're going to need to see from a customer would be your ML development procedure, how you do configuration management. For example, if you're training a model, how do you save the actual weights or the parameters of the model between different runs? If you're validating the results between multiple different models, how do you make the decision of which one performs best? How is that tested? How do you save all this information? How do you qualify tools? In machine learning, there are a lot of tools and libraries that are needed to do the learning itself. And many of these tools are very commonly used, but they're also not functional safety certified. So there's techniques for how you do software tool qualification, which is defined in existing standards. So how do you do that for your machine learning tools? And then what Exida is going to review is, does your machine learning design and development process, does it meet requirements from existing standards? Does it meet the requirements that Exida is defining as part of our ML scheme? These Exida requirements we're defining to help supplement our existing functional safety standards because, like we talked about earlier, we don't have published functional safety standards targeted with machine learning that tell you, these are the criterias or these are the areas that you have to address to achieve safe machine learning. And then again, looking at your ML design process, again, how is the model trained? How are those models saved? How are they validated and tested? So these are the types of topics that we'll go over in an ML process gap analysis. And really the key deliverable is we'll be able to give you early feedback about where the gaps are between your design process and what the standards and Exida are looking for. And it also helps you save time and effort so that eventually, if you are interested in pursuing certification, you've already had this preliminary review of your ML procedures. So we talked about advisory services, the ML, FMEA, and architecture review, and a process gap analysis. Now next, let's talk about analysis services. And these have to do with analyzing the model, the machine learning model, and its performance. Now the first technique, neural network architecture analysis, this has really been pioneered by my colleague Andre Rosbach in our German offices. Most of the models that folks are actually using in practice fall into this category of neural networks. And the way neural networks work is that you have layers of sequential computations. One layer could be a matrix multiplication between the data and a set of parameters, which are those weights that we've talked about. So one layer could be a matrix multiplication between your incoming data and some weights that you have learned that are inside your model. Then maybe you have a different multiplication. Convolution is a different type of layer where you're sort of filtering this data with a filter that you've learned. So there's lots of different types of layers. And in general, a neural network itself, it's a black box. So you have all of these different layers with these learned parameters, but you can't really visualize or inspect the layers. In general, there are some techniques to do this, but in general, it's not possible. And so really, with a neural network, what you're seeing is there's some input data coming in. It goes through these different layers of computation, which could be, hundreds of layers of computation, and then there's some output at the end. And so This makes it challenging to do safety analyses because you can't understand the thought process of the neural network. Now, if you think about those different layers of computation that are inside of the neural network, what happens is they get connected together in a graph, and that really defines the computation. It's called a computational graph. Now, typically, the way this computational graph is connected, it encodes some kind of human knowledge. Now, you can't necessarily understand the way all of the layers connect, but here's one really typical example. It's called non-maximal suppression. So in the network, you might be collecting all of these numbers, and at a certain point, you have maybe 200 potential detections. Then with non-maximal suppression, the code inside of the model will say, hey, you know what? I only want to keep track of 100 because I really don't think there are going to be 200 valid, interesting detections within this image. And so then only 100 detections are carried forward. Andre, my colleague, brought up this example. But so what happens then is you're making some kind of assumption about the task. And if you do a review of the computational graph and the code that's supporting the neural network, you can find that point and then review or assess, is this valid for my applications? What could go wrong if there are actually more detections? And so then now you've taken this black box model, but you're actually able to do some assessment of it. So that type of analysis is really what we're doing in this neural network architectural analysis. So as the input, what we need is the actual computational graph of the neural network. And what we do is we review the computational graph structure and the impact of the graph and the inspectable code that's included. So that example of non-maximal suppression, that's something that would be inspectable code. And so the key deliverable is we can provide some feedback on the safety implications of your specific neural network architecture. So that's something that my colleague Andre has really developed. Now, a different type of analysis that is also important is called statistical analysis. Now, we talked about how neural networks and machine learning models, you can't inspect how they're making decisions. Typically, you have these many layers of computations that include these learned parameters, and so you can see the input and you can see the output, but you can't really understand how they're making decisions. Now, what's really critical with these machine learning models after they've been learned is that they're performing the function you need them to perform in this safety critical task. And so the first step to that is defining some kind of performance target. So this is something that Exida would work with our customer, and for the specific application and their design, we would help develop or derive this performance target. And so this is really saying, hey, I need my model to perform this well to be able to achieve safety in this task. Now, for hardware, these performance targets are already defined by the standards. These are your SIL 1, 2, 3 architectural metric thresholds or probability of failure on demand thresholds. And in 26262, these would be your ASIL, single point fault metric thresholds or probability metric of hardware failure. So for hardware, these levels are already defined. They're not set in stone yet for machine learning. So this is where, again, that expert judgment piece comes into play. We need to look at your application, where it's going to be used, and kind of define this target. Then the statistical analysis, it's going to provide evidence that the model that's been trained or learned is actually meeting this target. It can give you insight into what is impacting your model's performance, and it can also give you insight into where it's safe to use the model. So one simple way you could think about doing an analysis of your model is testing it. You test the model, you observe the performance, and that gives you one measure. Typically, we want to be doing a bit more than that for the statistical analysis, and there are a number of different techniques that we can use for this. Bayesian nets, Bayesian analysis is a great technique for problems where you either know what different distributions of factors within the task you're interested in are, or you have a way to estimate those distributions. And you also can do design of experiments. Principal components analysis is a way to understand what key factors lead to differences in performance. And there's also a technique called network generalization prediction, which was actually the focus of my PhD thesis. So I spent several years of my life on that. So we have some experience on this network generalization prediction. The goal of NGP is to be able to predict the performance of your learned model in a new operating domain. This can help you understand if your model's performance is adequate for safety critical tasks, where you can use the model, and what your likely failure modes are. We have a webinar that actually goes into more detail about NGP. So if you're interested, I'd encourage you please check that out, and you'll see a little bit more detail about how that actually works. So for the statistical analysis, from our customer, we're going to need a description of the application and what they know or believe are going to be relevant environmental factors, a trained model and test data, and test results. And so what we will do as Exida is review a statistical analysis technique proposed by the customer if, say, for example, you have a certain technique that you would like us to use or that you have already performed. And we can help determine if that's going to be sufficient for what we need. We could also provide some guidance of what techniques might be a good fit for you. Then we can define a performance target and actually perform the statistical analysis. And so really the key deliverable here is an estimate of your model's performance, which is telling you how likely your machine learning model will be able to actually perform the task that we need it to perform. So in our analysis services, we've talked about both the neural network architecture analysis and this ML statistical analysis. Now next up are certification services. So this would be actually taking your trained model and certifying it. Now for machine learning, there are a number of different pieces we use to assess. So like I mentioned earlier in the presentation, we're going to keep using the foundations of functional safety. We want to keep using all of these techniques and ideas that have been helping keep hardware and software safe for decades. We have this artificial intelligence and machine learning assessment scheme that Exida is developing, as well as expert judgment applied to your specific design in your specific operating domain. And so we're going to evaluate the use cases for the model, what the functional requirements for the machine learning are, what the process requirements are, the defined performance targets, and the design verification, which would include things like the statistical analysis, but would also include, integration tests, all of these topics that we currently use in functional safety. We want to keep using those for machine learning. Now, for the process assessment, this is going to build off of what we did for the process gap analysis. So the top figure here is just showing that typically for machine learning, you might not follow all of the steps that we'd expect for functional safety. But at the bottom is an example process diagram for how you could have a development process that works for machine learning, but also meets what functional safety requires. And that bottom picture is actually from the draft technical report for 5469. So we're going to look at how you do the design and do that final process review. Next, we're going to look at your ML design lifecycle. So how do you define your ODD? How did you define your performance targets? How did you decide what data you were going to use for training and testing? Do you have enough data? How do we evaluate whether you've met the performance target with probably some kind of statistical analysis? How are you planning on monitoring your performance in the field? And then how does that feed back into what you've defined as acceptable, levels of risk? And then this is showing in a cycle that, typically we'll see that all engineering design processes have some level of iteration, and we expect that to be true with machine learning. So these are just some of the key topics we would look at, but of course we would go into much more detail. We talked already about doing statistical analysis, and so here we're just saying for certification, the results of that statistical analysis will come into play, and we will certify the models only in the context where we can show that those performance targets have been met. So what we very likely expect is that ML models will meet those performance criteria in some settings, but not in all. And so we're expecting that as part of certification, we're going to define, hey, these are our certifiable operating contexts, and here are the uncertifiable operating contexts. And so that the machine learning model, it doesn't have to be perfect everywhere to be used safely, but we need to understand where it's safe to use and where it isn't. And so for the actual assessment and certification from the customer, what we need is, of course, process documentation and design documentation. And as we even just talked about in those last couple slides, all of these inputs for these previous steps that we've done, these can help provide evidence for the eventual certification. So what you found in the ML FMEA, what the process gap analysis found, your neural network architecture analysis, and your statistical analysis, that all provides input to the eventual certification. And so then again, we're going to review the use cases, functional requirements, process requirements, performance targets, and design verification to be able to reach a certification decision. And so ideally, the deliverable from this step is going to be a certified model. Now, the last step that I'd like to talk about is integration services, which verify the machine learning model in a specific integrated system. So we talked about in the certification step the idea that for a given trained model, it might not be able to be certified in all of the initially thought about operating conditions. So we would then define in the certification step, here are the settings where it's safe to use the model. All of this information then gets fed into the integrator who's using this machine learning model in their system. So ideally, they're going to be using the model in the same settings that it was certified in, but potentially if the model needs to be used slightly outside of that zone, the integrator might need to define additional safety functions for the machine learning. How would somebody do that? That's a great question. So AI or ML safety functions. Just like in the typical process industry, a safety function is something that's going to intervene and stop a potentially dangerous situation. So for machine learning, these safety functions could be stepping in and maybe limiting the controls for the machine learning model. So imagine in an autonomous driving task, maybe if it's rainy or sleeting or snowing, the maximum speed that you allow the autonomous vehicle to drive at is lower than the typical speed. Or maybe in a robot manipulation task, if there are people around the robot, depending on how close the people are to the robot can move at different speeds, different torques, things like that. Another example could be a handoff between the machine learning algorithm and either a traditional algorithm or a person standing by. So these types of techniques are ways that you could add a safety function to a machine learning model. And then Now, the last technique that I want to talk about for integration is continuous monitoring. So there's this topic called dataset drift that we see very often in machine learning. And what dataset drift addresses is that over time, things tend to change. So maybe you recorded data and trained a model in 2019. It seemed like there was some big change that happened in 2020, and the world was quite different for a while. And then, slowly things went back to normal. But we see that over time, the distribution of data, the frequency of different things, they change. And so that can mean that the observed performance of the model in the field can become quite different over time from the way the performance was when you trained and tested and certified the model. So continuous monitoring, this refers to having some kind of automated monitoring or checking of the model as it's working. And so there are different techniques that you can use to do this. The way I kind of explain this is even these very complicated neural networks that have many layers, hundreds of layers, often they're really making a decision that's like seeing if this input data falls on one side of the line or the other. If it's deciding, can I drive or should I stop? Can I move or should I stay put? And how close some data maps to that deciding line, that's something that you can watch in different ways. And without having anybody label the data that's coming in or supervise and actually watch the model, there are ways that you can just detect that. And so what we're talking about here with this continuous monitoring is developing a technique with the customer for how you can watch how the ML is performing over time, and really, without even having to label if it's making a mistake or not, notice if the data that's coming in, if it's shifting, if it's changing. And so this will allow you to detect if the model's performance isn't sufficient, if you need to go back to an earlier point in the design process, and really gives you another layer of protection for using these machine learning systems in challenging applications. So for the input, what we are going to need for this system verification is the original machine learning model certification or some assessment about the machine learning model itself, the overall system design information, and the intended operating domain for the system itself. And then we'll review the certified machine learning context compared to the intended operating context, the safety functions if they're designed for the system, and a strategy for how you can do this continuous monitoring. And then this will help Exida determine if you can safely integrate machine learning into this final system. And so really then what this achieves is verification of your whole system together, including your machine learning piece. So like we saw for integration services, we're looking at system verification with ML continuous monitoring. So these services together really form the offering for safe machine learning at Exida. So we looked at advisory services, analysis services, certification services, and integration services. And we're expecting that all these are going to be available starting in Q1 of 2024. So thank you so much for your attention, and I'll be happy to take any questions that you have.